Let's do a physics problem. Let's do a problem from this. Let's do a problem from the rotation chapter in this book on page 207. We're going to do problem 51. And in problem 51, we've got a couple of blocks hanging over a pulley, and we got a bunch of questions about these blocks hanging over the pulley. And the first is how fast the blocks are accelerating. This is pretty straightforward. So I've written in some values here. We got a half-kilogram block, and so it's a little less than half a kilogram block. And the half-kilogram block falls 3/4 of a meter in 5 seconds, and we've got to be able to figure out the magnitude of that acceleration. That can't be too hard. So let's see. So we know that this is just some linear movement. So I've got whoa, that's a fat pen. Let's try something less fat. D is equal to 1/2 AT squared, because this starts with a V naught equal to 0, and so I've got 3/4 of a meter is going to be equal to 1/2 A times 5 squared, and so A is going to be 2 times 3/4 over 25, I think. And let's see, that's a 2, so 3/50. So A is going to be 3/50 or 0.06. Is that right? 3/50 is the same as 6%. Yeah, 3/5 of a meter per second squared. All right. So the next thing that we want to find out the tension on the two pulleys, tension 2 and tension 1. And this would be a good moment to ask, wait a second, what's up with these different tensions? Like, it used to be that, this tension here was the same as this tension here. That was the whole idea of an ideal chord. But now that's not going to be the same, because in this case, our cord runs up and over our pulley, and the cord has to have some friction with the pulley, because we're told that it doesn't slip, right? It says without the cord slipping on the pulley. So the cord doesn't slip, and the pulley is going to have to rotate, because the pulley now has inertia, right? Before we didn't have to think about the pulley's inertia. Now we got to think about the pulley's inertia. And because the pulley has inertia, the torque that's pulling it in this direction had better not be the same as the torque pulling it in that direction. Those two torques can't possibly be equal, otherwise the pulley's not going to turn. Well, if that's going to be the case, this tension over here, T2, cannot possibly be equal to this tension over here, T1. So we got to figure out what those two tensions are. And happily, this problem is set up in such a way that it's pretty darn easy to do that. How do we do that? Well, we call on our Newton's second law skills, and we go like, all right, I got a free body diagram for my first mass, and it's got T1 pulling up, and it's got weight 1 pulling down, and this is going to be 0.46 G pulling up, and that's T1 pulling up, and we know that the net force in Y on this should be equal to the mass times the acceleration. Well, we know the mass, we know the acceleration, so we can say that we know we're accelerating up at, I forget. Okay, so if that means if the yikes. So if the acceleration, if that guy there is accelerating upward at 0.06 meter per second squared, then T1 minus, I'm going to say 4.6 newtons is going to be 0.46 times 0.06, and we ought to be able to figure out what T1 is here. So that tells us that T1 is equal to 4.6276 newtons. we ought to be able to figure out T2 by the same trick. Here we've got a mass of 1/2, we've got T2 pulling up, we've got 0.5 G pulling down, and the net force is equal to MA. So here we're accelerating downward, and so 0.5 G minus T2 should equal the mass of 1/2 times our acceleration, which is 0.06. And T2 is equal to 4.98 newtons. Next thing these jokers want to know is the angular acceleration of the pulley. And at this point, we know the tensions that are pulling on the disc, but we also know this other thing. We know that each one of these blocks is accelerating. This block is accelerating down. This block here is accelerating up. And we know their rates of acceleration, that this acceleration is equal to 0.06 meters per second squared. Well, this acceleration here has got to be the same as the acceleration of a point on the rim, the tangential acceleration of a point on a rim. Now, we remember that that little point there, it's complicated. This point is doing two things at once. It's moving faster in a tangential direction, right? It's speeding up. It's speeding up in the rate at which it is going around in a circle. And at the same time, it also has this acceleration toward the center, this centripetal acceleration, the acceleration that contributes to its change in direction. But we're not worried about the centripetal acceleration right now. That was not what was supposed to go away, darn it. Anyway, we're not worried about the centripetal acceleration. We're just worried about how fast it's speeding up here, its angular acceleration. And the angular acceleration, we know, it can be linked to linear acceleration in this very neat and tidy way. We know that alpha is equal to the tangential acceleration of a point divided by how far that point away is from the axis of rotation. So we can say, all right, we've got an acceleration of 0.06 meters per second squared. That's the point that's doing that accelerating. It's this point out here on the rim. And we also know that is some distance 0.05 meters from the axis of rotation. So that's an alpha of 6/5, which I should be able to do in my head, right? Because that's 6/5 is 1.2 radians per second squared, I think. And I'm going to be fancy and write that seconds to the -2 because we all know that radians aren't really a unit. They're just they're a placeholder. And lastly, we're supposed to figure out the rotational inertia. We're supposed to figure out what the rotational inertia is of this thing. Well, we're going to find out the rotational inertia by applying Newton's second law for rotation, because at this juncture we know what the forces are. We like, this force is pulling the pulley this way. This force is pulling the pulley this way, and we know the pulley's rate of angular acceleration. And so we can apply Newton's second law for rotation, which says the net torque, and I'm not writing net, but you know what I'm talking about. The net torque is equal to the moment of inertia, the rotational inertia, times alpha, or we're going to massage this around because we want the rotational inertia, so I'm going to say that's going to be I is torque over alpha. So now we need to find out the torque. So let's look at the way the forces behave. I'm going to say, and change to a red pen to do a torque diagram. So here's one torque. This is a torque in this direction is this force right here. And I try to draw a torque that has both the moment arm, both the lever arm, and the force in it. So this torque, which is a anti-clockwise, a counterclockwise torque, is going to be the length of the lever arm times that force. And then we've got another torque over here. That's also the length of the lever arm times that force. And if these two forces had the same magnitude, this wouldn't go anywhere. But they don't have the same magnitude. So I think we should be able to work this out. Come here, blue pen. So that means that I has to be equal to the net torque, which is going to be I'm going to call that clockwise torque positive, and so I'm going to say 4.98 times that length of that arm, which is 5 centimeters, minus the torque in the other direction, 4.63. There were more decimals, right? 627, also times 0.25, and all of that divided by the alpha, which is, what did we say? It was 1.2. Grab a calculator and we work that out. And so according to this, the moment of inertia is 0.014, that was 147 kilogram meters squared. And we're going to say that is the rotational inertia of this disk. And I have not looked up the answers, so I'm hoping that this agrees with the answers, but that's my answer, and I'm sticking with it.